Hello everybody and welcome to our next chapter, Physics Chapter 3. And in this chapter we are covering thermodynamics. So the first important thing about this chapter are the laws of thermodynamics. So the zeroth law of thermodynamics states that when two systems have the same average kinetic energy, they will have the same temperature, which means no heat will be transferred. But until that point, one system is always going to be giving heat off and the other system is always going to be receiving heat until they reach thermal equilibrium. The second law of the first law of thermodynamics is that the total energy of the universe does not go up or down. And this is also an important equation. So delta U equals Q minus W. So that is saying that the change of energy in the delta U is the change in the system's internal energy equals the energy transferred into the system as heat minus the work minus work. All right, and so if we go down here, the Q values and the W values are important. So positive Q value means heat is added to the system. A negative Q value means that heat left the system. A positive W value means that the system did positive work, and then a negative W value is the system does negative work. So another and last law of thermodynamics is the second law, and it states that in a closed system, energy will spontaneously spread out. And we even also know that is entropy, and we show it over here a little bit. So high entropy means more disorder. It means, as a gas, for example, has more entropy compared to a solid where the particles are not as spread out. So it's just the amount of spreaded outness that the particle has. So that is entropy, and that is what we see in the second law of thermodynamics. Same thing. If you have like food coloring, for example, in water, you drop one drop of food coloring in the water, it doesn't just stay in that one place. It like disperses and diffuses in throughout the rest of the water, and that's what happens, with gases and of that nature. So that's when we're talking about entropy. Another thing to note is thermal expansion. So sometimes when things, are heated, they expand. We see that. That's why our sidewalks has cracks. So that they can expand without cracking. And so there can be a change in length or a change in volume. So the change in length is alpha times alpha L delta T, and the change in volume will be beta times volume delta T. And so some of those constants will be given in the question. So let's move on to our types of heat transfer. So there's conduction, which is when two solids are in contact. Then we have convection, and that is the circulation of fluids. And then we have radiation, which is the emission or absorption of electromagnetic energy. Okay, and that we also have types of systems. So we have an isolated system that does not exchange energy or matter with its surroundings. We have a closed system that exchanges energy but not matter with its surroundings. And then we have an open system that exchanges both energy and matter with its surroundings. And this brings us into our state functions and our process functions. So our state functions, for example, enthalpy, density, those kind of things are pathway independent. Okay, but stuff like heat and work are process functions, and they are pathway dependent. So it's kind of like the displacement versus distance. Those are kind of a way to look at it. Instead, if you're going from here to the top of the mountain, the pathway independent is saying, okay, what is your displacement from the top to the bottom? Okay, that would be your pathway independent things. And then the pathway dependent, for example, would take into account the whole pathway that you take to get up to the top. So those are our two kinds of pathways that we're kind of dealing with. And then we have our processes with constant variables. I'm hoping you can see the graph over here. Move it a little closer. There's a light glaring, so I'll have to turn it sideways. All right. So here we have our processes with constant variables. So we have, these names are kind of self-explanatory. So we have isobaric, where the change of pressure is equal to 0. We have isothermal, and there the delta U is equal to 0. We have adiabatic, which is where Q equals 0, so the heat transferred equals 0. Then we have the isovolumetric, which means that delta V is equal to 0. And an important part with this one is that this means that the work is also equal to 0, okay? Because the work of a gas is negative P delta V, okay? So if the delta V is equal to 0, then we know the work of the gas will be, no work will have been done. And so this is a graph to demonstrate those processes. This is the first isobaric, this is the pressure, this is the volume, this is the isobaric graph, the isothermal graph, this is the adiabatic graph, and then this is the isovolumetric graph. So another thing to remember is the ideal gas law. So PV equals nRT is always important and will definitely come up. And then we have, let me move it over here again. There you go. All right, hopefully. Oh, there we go. So the heat is actually the transfer of energy, while temperature is the measure of the internal energy of a system, okay? And so the temperature does not change between phases. So if there's a phase change, the temperature is not changing during that phase change. And I believe, we just have one more thing to cover down here. Hopefully you can see it. So that equation down there, Q equals MCAT, Q equals MC delta T, is also a good equation to remember. There we go. Where Q equals the heat, M equals the mass in grams, C is the specific heat, and delta T is the change in temperature in Kelvin. So those are all important things to remember when you're going into physics chapter 3, thermodynamics, and stay tuned for our next video.